All right, so how you guys doing today? You okay? Oh, I'm good, thank you. All right, so let's continue on the chapter 17. So we talked about the alcohol compound, or phenol, can be either weak base or weak acid. Okay, so we learn about the induction and other sorbation problem for making slightly even stronger or weaker acid compounds as an alcohol. Okay, so sometimes it behave like a weak acid here, meaning it only going to interact with the strong base or some alkali metal, which is always love to donate the electron. So the here's some example we can try. You have a top. This is so if you have a top butanol, okay, and we have some the alkali metal like a potassium over here, okay. So then we actually going to expect maybe you can have two of each over here. What you can expect here is the top butoxide. Once you have that hydrogen leave from there, they will pair with the potassium cation over here. Okay, and then you're going to have the hydrogens were being reduced. So this is the what happens when you make this one behave like an acid, donating the protons become as the alkoxide form, ion form, and then this will become eventually ionized to be paired with this the potassium butoxide or butanolate compound here with this the other product as well. Okay, so this is one example that alcohol can interact with the alkali metal. We can form some alkoxide form with the other products. Okay. All right. So and also interact or direct with the strong base. So if you have a methanol here, okay. So if it works as behaves like a weak acid, you can also try with a very strong base like sodium hydride over here. Okay, so as you can expect from here, we can also make some the alkoxide form after donating the protons will become methoxide here without the proton here and this oxygen here. Eventually they're going to pair with this sodium cation. Okay. And then these two will make also hydrogen diatomic molecule. Okay. So this is the strong base. You have a weak acid in your alcohol compound. They can also do this type of interaction here. It's a weak acid and strong base interaction. Okay, we have let's do just one more. Okay, if you have ethanol over here, and we have also very strong the sodium amide. This is very strong base, really strong base. And then can you actually do this for me real quick? So try to think about the alkoxide form of this one pairing with the cation part, and we'll pick up the hydrogen here. So if you do that, okay, 1 or 2 minutes, you can try. Okay, try to think about the alkoxide form of this one pairing with the cation part, and this will pick up the hydrogen. Okay. So weak acid and strong base interaction. 30 seconds, reduce together. So alkoxide form of this one paired with the cation, and it will pick up the protons. Okay. So yeah, so if you look at this over here, right, this is basically what happens, right? Okay, and then this will donate the protons, then it will become this one. Okay, see this one here. So these two can pair with the sodium hydroxide form, and this one pick up this one, become ammonia. So this will become this one. Okay. There you go. See, right? Good. Yeah. So then let's do a little bit of different one. Okay. So this is also the weak acid strong base, but no, well, different reaction actually. But if you have a cyclohexanol here, you can also try to use the greener reagent here. So we have a RMgX form of the reagent. It's a greener reagent. Maybe you can try to use one example. Okay, this is a halogen, this is any R group, so we just use a methyl type of alkyl group with the halogen, which is our bromine. This is what it shows here. And then if you look at this one over here, this will also behave like a weak acid. So you can actually look at this one as this one over here. The thing is you see this one, magnesium here is metal, right? Magnesium is metal, right? So if you think about they break apart, this will be slightly positive because it's a metal. That's the characteristic metal. So this is organic. So relatively speaking, it's a bit more negative. So when they break apart, they become like this, okay? And then they become positive because of the this metal here. And then when they do this, okay, so you can have so this is a bit different from what we did for the previous three, but this is something you can. So some greener reagent, this is what we learned before in the Orgo 1, but you can also use that for this type of weak acid kind of behavior of the alcohol compound. Okay, so how about the phenol? Okay, this phenol has a weak acid because we talk about not just alcohol but the phenol too, right? So phenol you have. So I'm gonna do the same thing over here. I'm gonna direct this one with the strong base. So I'm gonna do sodium hydroxide, which might be very strong base. Okay. So as you know by now, you just need to have the alkoxide form with this one. Phenolate here, and then you just need to pair that with the cation, which is the sodium. Okay. Alkali metal hydroxide is very strong base. And then, as you know, this breaks apart. Okay, so this is what actually happened, right? So that's why it become positive. Okay, so then this hydroxide. So it is indeed fact that also phenol can behave like a weak acid as other regular alcohol. It's pretty much the same. So makes sense, right? You good? Okay. So yeah. Can I move on? Right. So if that is the case, there's one more thing I want you to remember. So for example, if you have here. If you have this one actually. You have a natural group on this phenol base over here. And in this case, you can assume that the acidity of the one that with the some group, which is electron withdrawing groups, will become a stronger acid than the other. So acidity wise, this will become stronger than this one. So here's the reason why. Why does it become stronger acid than this one? Okay. So that is because of the much stable form it can has as a alkoxide form. So if you let's think about this one now, donating the protons. This one is also donating the proton over here, but this one they can do some additional work to make them even more stable. So what they can do is they can actually do. I'm gonna show you several the rearrangement of the pair of electrons, but I'm probably not going to show you all. But just so you have 3 lone pair in this oxygen. That's why it has become negative, because oxygen is group 6. So if you have this one over here, what they can do is they can actually move to lone pair of electron down here. Okay, so then this will electron pair of electron. This one here will go to here. So you see the pair of electron here will go here. So it can So the you see now it moved, right? So you just we just rearranged the pair of electrons that in the lone pair from previously onto the double one here. So that push, because you can have a double one here and here, because it's it's impossible for carbon especially. And so we move to here, okay, right? And then you can try to move this one to move the negative charge over here, okay? And then you can actually get the negative charge over here to move here. So it will become negative charge. It comes down and it pushes that to the here, and you can push down to the here. And then you can push down to here to move this here again. So you see the negative charge here with the lone pair movement here down here, right? And goes here, 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 here. So they can actually move around in the many other resonance form, which is because this is the electron withdrawing groups. So this is able to getting the electron into the groups, and they can put it back into the other parts of the compounds. That all kind of evens out and well with the locations. Okay, so in this whole compound can be all possible for the resonance structure, meaning they all become delocalized. So you guys remember delocalized? So delocalized simply means you cannot locate the electron anymore, because there's electron here, there's some, but since we can move the electron in the very evenly on all parts of the compounds, then we can actually need to use a probability to find the electron, because it could be anywhere, because it's all possible resonance structure with the electron withdrawing groups on here. Okay, so that makes electron delocalized simply means if you have electrons only here, not here, this will be very unstable, right? Because you have electrons concentrated on one part of the compounds, the other is not. They'll make what? Some electrostatic force to be unstabilized, because it's chargely potential-wise different. Okay? But if you can distribute the charge equally on all parts by just moving it with the all possible resonance structure, they can be delocalized. Meaning you don't have to just put it in the electron on one side, but just put it everywhere. So we don't have to know how many numbers of electron each carbon or nitrogen oxygen anymore. That would make this compound will have a more, relatively speaking, evenly electrodensity-wise spread out nicely. Then there'll be less electrostatic interactions on each atoms in the compound. That makes this one more stable. Makes sense, right? Somewhat makes sense, right? So meaning, what it really means that, this one will be, relatively speaking, more stable when they donate the protons than this one. Then they don't mind donating protons than this one, because they can be somewhat stable still. Even though they're donating the proton, they'll be still somewhat stable because of that. So this will be, relatively speaking, stronger acid than this one, because this one will give us more protons. Because even though they become an alkoxide form, relatively speaking, more stable, meaning they don't mind to give more numbers of proton than this one does, because this one may not, because it still does as a weak acid, so meaning it's a small amount of the proton donating here, but this one, well, I can do better than him, so then they can donate more protons and become more stronger acid. Okay, so the point here is, you don't have to know how to draw the resonance structure here, but just the one that has the electro-withdrawing groups and this part would make one more stronger acid. Okay, so yeah, I'll give you one more example here. Okay, you have a phenol here. You have a para-hydroxy benzaldehyde here. Which one do you think is stronger acid here? This one or this one? This is 1 and 2. Which one will be stronger acid? And by the way, this is also electron withdrawing groups. So which one will be the stronger acid, do you think? 1 or 2? 2, yeah, perfect. That's it. Okay, so that's all you need to know for the exam. So you see this, the groups that has the electro-withdrawing groups that make this one more stable in alkoxide form we just did previously today and Monday. That also factor acidity of the alcohol or phenol compound. Sounds good, right? That's all you need to know. Alrighty. Can I move on? You good? Okay. Yeah, so once again, do not worry about too much about the mechanism. You only need to know the, yeah. All right, so let's try to do some review on the how do you can make some alcohol compounds, which we kind of did in over 1 slightly, but we can do more here. So if you have a borane, okay, with the tetrahydrofuran solvent, I hope you guys remember this. They actually coming into the less hindered region, which means I'm giving this example because it has 2 carbons with a double bond, but this side is more like crowded with the methyl groups here. This is not. This is what we did. So if you have a methyl group, the borane will coming into this side because it's the spacing problem right here. So the borane will actually coming into this side. And then hydrogen, one of the hydrogen with it actually makes some semi bond, and now they actually make this. Okay, so this is what we did over 1. Okay, so that makes So this is why it coming on to this part over here. Okay. All right. So if that is the case, that what you can do is you actually going to have so if that is the case, you can treat it with the peroxide, okay, hydrogen peroxide. Do you want to know the mechanism, or can I just move on? You don't have to know the mechanism, but what it does is they actually switch this one to the hydrox group. So so I'll just briefly explain. This will become this one, and then attached to this one initially, but later they're going to switch to the bond to the oxygen, and detach this one and this one later become hydroxide. You don't have to know, but this is the one way we can make the alcohol compounds using chlorine compounds. Okay. All right, the next one is the okay. So next one is the oxymercuration. So you have this one. And then you just need to do is if you do this one over here, this is also one thing. They become this one. It's one apart because there's initially 2 acetate, mercury 2 acetate, but they become this one over here, and then they actually attach to here. Then over here, and then what you can do is so this is the way you can have water comes in. So let me explain this briefly. So this one comes in here. They make so you don't have to know, this is just a review. So they're coming into here, but they detach from this side here. So you can have a more stable carbocation position here. See, this is more substitute, right? This position here, than this one. So then this one can be attacked by water to leave the hydrox group. So when water comes in, and then there's another water can grab this one, goes there. So So then this will become hydrogen cation, but this will become the hydrox group. Okay. Do you guys remember this? Kind of. So anyway, so once again, you just need to know what happens to the compound. Okay. So if you have sodium borohydride, so if you remember, sodium borohydride is really good at locating the hydride. So because if you look at the sodium borohydride anion here, this will have a hydride. We'll switch this one, your mercury acetate group over here, so it becomes like this, because this were just switched by the hydride. So as you know, we don't have to show the hydrogen, so it's so this is another way you can make some alcohol, but the difference is the previous one is where you can put the hydroxy group away from the less substitute. This is where you can put the hydroxy group on the more substitute position of the carbon. Can I move on? Make fun. All right, so the okay, so the next one, okay, so you can have over here, and if you use the azumium tetroxide, okay, over here with some pyridine, organic solvent or other things, what you can do is you can actually going to add. They're coming onto the same side. They're coming onto the same side. So what happens to this one is in this one, okay? And then because of this compound coming on together, right? Because these two oxygen were having on the same side, it has to be on the same side, okay? So then you can treat it with the sodium sulfide with some water, but we can assume already the water there. So then eventually this like a cis-diol compound. So in this way, not even just one hydroxy group, you can put two with this one. But the thing is, because of this aluminum tetroxide coming in the same side, they will be located, these two diol will be in the cis position. They're on the same side. So that is the thing. Do you guys actually remember this one? Okay, good. So let's move on. Can you guys actually do this one real quick then? Maybe if you treat it with this one, okay? I just do the same mechanism here, but maybe okay. Can you guys estimate the product real quick, and now move on. Just make sure you put in the two hydroxy group where you had a double bond, but you will be on the same side. That's the key. Okay? About 1 minute, and we'll do this together. Okay, 30 seconds, we'll do this together. So there will be two hydroxy groups, but you're coming on the same side where you had a double bond between two carbons. Okay, that's it. Okay, so you can compare this one to your answer. Okay. You got it right? Yeah. Perfect. So let's move on. All right. Okay, so if we try to do, maybe we want to put it in the opposite side instead of the same side, what you can do is also this one with the dichloromethane solvent here. So this is a peroxy acid here. The one we discussed in OGO1 was the metachloroperoxide benzoic acid. So what it does really is just they're making an epoxide. So this is a quick review. Okay. Over here, and then you can treat it with some acidic condition over there. Okay, so what it does is they break apart over here, so they can go in this way, but because of the epoxide, the cyclic form on this side, they're coming to the back side of that. So that makes so once they become negative, because it's getting this one, but now the methyl group pushing to this side, because previously they were in the back side because of the epoxide on this position, but they no more cyclic structure with the oxygen epoxide no more when they break it, so they can come in this way hydronium. Okay. They're coming in this way, and then they're coming on the back side, right? So it will be not on the same side anymore. And then this water, once water comes in, this will be gripped by another water. So this will be neutral, so it will be hydroxy group. And this now push the back again, because now you don't have a epoxide. So as you can see, you also have a 2 hydroxy group on this alkene compound. You made an alcohol compound, but only difference from the one we did just before is they're on the opposite side. The hydroxy group is the opposite side. The methyl group and the hydroxide is actually on the same side, right? But the addition was on happen more like anti-stereochemistry wise. Okay? Makes sense, right? Because of the epoxide, it makes the anti-addition. Okay? Can I move on? All right. So that was a good review. Okay? So let's try to do some parts of the chapter 17. So whenever you do the reduction, we also discussed in this one a lot in the OGO1. But technically, when you do have a hydrogenation, when you have some more, so if it's R group, this is the aldehyde, this is a ketone, right? So this is the aldehyde, this is the ketone. If you try to reduce the compound, simply meaning you just want to do lots of hydrogenation. So normally we do put as like capital H in a bracket. This is what you can say, oh, we try to reduce the compound. That's what it really means. Okay? Same thing over here. So if you want to do actually either oxidize the compound, we do this one. So just the capital O with the bracket, that means it will be going through the oxidation. But here, we do reduction here. So whenever you do the reduction on this one, what it becomes is you have carbons, have another hydrogen coming into this carbon here, and the carbonyl group will have lose the double bond and getting hydrogen on this oxygen here. So it will become the hydroxy group. So when you actually try to reduce your carbonyl, or you can say aldehyde or ketone or other compounds, the carbonyl groups, they can become alcohol. So this is also another important thing. So if you look at this one here, if you try to reduce the primary, because you only has one R on this here, so this will become primary alcohol. Okay. But if you try to reduce the ketone, you can make this one. So it will become secondary alcohol. So okay, let's do a bit problem here. So how are we gonna reduce the compounds with the aldehyde or ketone? So if you have something like this one. We just did this one too, but if you think about the sodium, the borohydride, okay, with some acidic conditions over here, this will actually transfer hydride right on the carbon with in the carbonic groups over there. So then, if you think about this one. Now it has another hydrogen over here, and this one will actually push the one pair electron, especially on the p orbital, will go to that. So push, so become no single bond, but this one will have a 3 lone pair then instead of 2, so the negative charge. Okay. So then later in an acidic condition, they can pick up the obviously hydrogen. Okay, so it will become this one. Okay, so indeed it will become what? Primary alcohol, as we did with the aldehyde. With this reduction, you have a primary alcohol. Okay. Makes sense, right? Okay. Let's do one more, and I'll finish it. So how about ketone? So we had a ketone here, right? Okay, this is a ketone because you have 2 R groups over here. So I'm just gonna do the same thing. So sodium borohydride and also the acidic condition. And then so the hydride will actually donate from the borohydride, and then goes up and makes positive. Pick up the one under this one, become this one. So as you can see, if you do this one, you have a, oops, my drawing is really bad today. So they become this one. So as you can see, this will become secondary alcohol. If you do the reduction on the ketone, you can make the secondary alcohol. So this is kind of proving what we had in the theoretical. So another thing, yeah, there's another way to reduce the compound, but we'll do this on Friday.